Well, most times we will be given a data value and we want to find the area under the normal curve with respect to some region. Sometimes we are given the area under the curve and we want to find the data values that would correspond to certain areas. And remember, the area under the curve of normal distribution also connects back to a probability, a proportion, or a percentile. So sometimes I'm given probability and I want to find out what data value would generate that probability. So it's kind of going a little bit backwards on the curve. So how can we use table A to find a z-score if I know what area I am looking at? So in our first example, it says find the z-score such that the area under the standard normal curve to the left of that z-score is 0.2. Alright, so I'm going to sketch what I'm looking at. Alright, so I'm going to sketch a normal distribution, and because I'm looking at the standard normal curve, I know its mean is 0 and its standard deviation is 1. Now, an important thing to keep in mind is that this curve is symmetric and the total area under the curve is 1. Okay, so it's helpful to remember a couple of these things when you go to mark your curve. So if the total area under the curve is 1, with the relationship to my mean, which is going to be halfway through my curve, the area to the left of the mean is 50%, or 0.5 if you wanted to write it as a decimal. The area to the right of the mean is the other 50%, or 0.5 if you want to write that as a decimal. All right, where the total area under the curve is 100%. So what we've just said is that with the relationship to this mean marker, half of the area is over here and half of the area is over here. When we're looking at the values that are in table A, since table A always gives me area to the left, if I am given an area that is bigger than 50%, I know I'm going to be over here, right? Because if this is 50% is from my mean left, and I'm looking at a value that is bigger than 50%, I know I have to have 50% plus a little bit more area. So I'd be looking at a positive z-score when I go to my data table, is what I would expect to find. If I know I'm looking for an area that is less than 50% or less than 0.5, then I know I must be over here to the left of my mean, because that would be then all the values that have an area of less than 50%. On this problem, I'm looking for values such that the area to the left of it is 0.2. Remember, 0.2 is the same thing as 20% if you wanted to write it in a percent form. So 20% of the area would be, all right, so that's going to be somewhere to the left of 0. And what they're giving me is they're giving me an area. Now, you don't want to label that 20% along that horizontal axis. That axis is very special. It's reserved for just our z-scores. So that's not where I want to label my 20%. So I would always recommend that when you're labeling your areas, you label them above the curve and maybe draw an arrow to like the shaded region that you're looking at. So this shaded region right here is 20% or 0.2. And then the question for me is, who is this z-score? Who is that marker such that the area to the left of it is 0.2? All right, so to the table. Now remember, when you're looking at these table of values, the areas are what is given kind of in the heart or the center of the table. And what you're going to be finding along the left edge and across the top are your z-scores. On the problem that we're looking at right now, I'm giving you the area and I want you to find the corresponding z-score. All right, so we're going to be looking in the heart of the table. It's going to be kind of a search. We're going to be looking for the value that is closest to 0.2 that we can find. All right, so kind of zooming in on this table then, looking for values that are at 0.2. I expect my z-score to be negative, so I'm going to be looking on the values that have like the negative z-scores. And I'm looking through here. So here's, like, for instance, 0.1977, and then here's 0.2005. So this value right here is really, really close to 0.2. It's just a little bit over it than it. The 0.1977 is further away. So the 0.2005 is going to be a pretty good indicator for what z-score I want. So I'm going to find out what is the corresponding z-score by looking over to what's going to be on the left column and what's going to be at the top up here. So to get an area of 0.2005, the z-score needs to be negative 0.84. So that's the z-score I want. So again, we found the area in the table, kind of looking in the heart of the table, was 0.2005, and it corresponded with a z-score of negative 0.84. So this is what I want. That's what I'd expect to have right here, such that the area to the left of it is 0.2. Alright, let's try another one. Let's find the z-score such that the area under the standard normal curve to the right of that z-score is 0.35. Alright, so again, sketches are wonderful. Let's see what's going on here. So we're working with the standard normal curve that has a mean of 0 and a standard deviation of 1. I want to find the z-score such that the area to the right of it is 0.35. Now, with relationship to my mean of 0, the area to the right of that would be 50% or 0.5. I want that to be less than 50%. The area that they're giving me to the right is 0.35. So it's going to be less than 50%, so I'm just going to put down a random marker, maybe right here. Maybe right here would be the z-score such that the area to the right of it, so this area right here, is 0.35. Who would that z-score be? Now remember that the table only gives us the area to the left. So if I know that this area to the right of this desired value is 0.35, then what would be this area to the left? Okay, how much area is that? So the area to the left would be 1 minus 0.35, or 0.65. So that's the value I'm going to start looking for in my table. What is the z-score such that the area to the left of it is 0.65? I expect that z-score to be positive, right? Because it's going to be to the right of 0 looking at my curve. All right, so again, to the table. And once you start looking in the center of the table and you try to find an area of 0.65, you're going to find that you're not going to get it as you're looking at these negative z-scores anyway. So come over here to these positive z-scores, and remember that we're trying to find 0.65. So then we would just start scanning through all of these numbers until we could find 0.65, or the closest we could get to it. So looking at this, that looks like really close, 0.6517. The other value that's right next to it is 0.6480. All right, but looking at that, that would be 0.002 away from my 0.65, and the 0.6517 is only 0.17 away. So that the 0.6517 is closer on a number line. Okay, maybe to kind of show you what's going on. All right, the value I want really is 0.65. In my table, I see a 0.6517, and I also see a 0.6480. The 0.6480 is 0.0020 away. The 0.6517 is only 0.0017 away, so this value is closer. So that's the one I'm going to grab out of the table. Now, by the way, if you have two values that are equally close, like if the value I was looking at was halfway between the two values I could find in the table, you would just take the mean of the two values in the table. Remember, you just define the mean, you add them up and divide by how many there are. So, but that's not the case here. There was one that was a little bit closer, so that's the value we're going to use. In any case, the z-score is 0.39. Alright, so that means the z-score I want right here is 0.39. That's the z-score such that the area to the right of it is 0.35, or using our table we found that the area to the left of it was 0.65. So that is my z-score that I want. Alright, so that would be finding a z-score if I'm given the area to the right. What about if I'm given area in the middle? So for the last one we're going to look at, it says find the z-score that separates the middle 94% of the distribution from the area in the tails of the standard normal curve. Alright, so again, we're going to start with a sketch so I can kind of see what's going on. Sketch a normal curve. You get really good at sketching curves when you do these types of problems because you're going to sketch a new curve for each problem. Since I'm looking at the standard normal curve, I know the mean is 0 and the standard deviation is 1. Alright, so I want to trap the area that's going to be in the middle 94%. So this is the region that I'm looking at, such that this region has an area of 94% or 0.94. And then the question that is being posed to me is who are these standard deviation markers down here, or what are these z-scores rather down there that would create this 94% of area in the middle. Alright, so now one of the first things to notice on this is if 94% of the area is in the middle, then how much area do I have left remaining to be in the tails? Well, 6%, right? Because I need the total area to be 100%. So if 94% of the area is in the middle, that leaves 6% of the area in those two tail regions, out here and out here to the left and the right. Now this curve is symmetric. Okay, so because of symmetry, each tail would have half of that remaining area. So because of symmetry, each tail has 6 divided by 2, or 3% area. And 3% as a decimal would be 0.03. So this area right here is 0.03, and this area right here is 0.03. So let's find the z-scores that would have these kind of area requirements. Let's start over here to the left because my table already gives me area to the left, so that one's going to be a little bit easier. So for this guy right here, this left z-score, the area to the left of it is just that 0.03 that we've marked. We would expect it to be a negative z-score because it's to the left of 0. So let's go to table A and find it. So we're going to go to those negative z-scores, and I'm going to be looking for 0.03. So 0.03 as I'm running through here. Here's 0.0301. That's really close as an area. So that z-score corresponds to negative 1.88. Alright, so in the table we found the area, I'm just recording what we found. We found the area that for 0.0301 has a z-score of negative 1.88. Okay, so that would be the z-score over here for the left part. What about this value over here that's on the right? So for this right most value, the area to the right of it is 0.03. But remember, our table wants area to the left. So with respect to this other z-score value I need to find, the area to the left of it is 1 minus 0.03, or 0.97. And if you didn't want to do it like that, you could just say, hey, with respect to this marker, I want all of this area. That would mean I want the 94% that's in the middle and then the 3% in the tail. If you add up 94 plus 3, you get your 97%, or 0.97 as a decimal. So it's just another way to think about it. Okay, it also works. In any case, once I know my area, which would be the 0.97, we would expect it to be a positive z-score because it's to the right of 0. Go to the table. 0.97. All right, so here we go. So looking at the positive values, 0.97, trying to find the value that's closest to it. This one right here is 0.9699. Yep, that's really close to 0.97. The next one after that is 0.9706, which is a little bit further away. So that corresponds to a z-score of 1.88. Alright, so this one right here, we found in the table, we found the area of 0.9699 has a z-score of 1.88. Alright, so these are the z-scores I want. It says find the z-score, should be z-scores rather, that separate the middle 94% of the distribution. Those z-scores are negative 1.88 and positive 1.88. And because we are having a mean of 0, and because the standard normal curve is symmetric, this is actually a cool thing because the area that I wanted over here to the left and to the right was the same area. It is actually going to be always a thing where if you could find the one value, the value on the other side is the other sign. So once I had found that negative 1.88, because the area to the left of it is 0.03, on the standard normal curve, if I want the value where the area to the right of it is 0.03 as well, and then it would just be positive 1.88. So you're going to find that that's actually always going to happen because of the symmetry of this curve.